So the final thing that we want to do is talk about hand calculating the between subjects t-test. And I often joke that this is a good skill to have if there's ever a situation where you don't have access to computers or calculators, some kind of apocalyptic event where you're still wanting to do statistics. However, it is important to remember two things. One, that this is actually how these tests were done up until the invention of calculators and then later computers. But also, it's a good idea to, at least with the more simple inferential statistics, walk through this process to have a better understanding of what is happening mathematically in all of our inferential tests. No matter how complex the test is, generally we're looking at effect size, for example, mean 1 minus mean 2, divided by total variance. And in this case, the equation, which is fairly similar to the Cohen's d we already learned, is the top of the equation is the mean of group 1 minus the mean of group 2. And the bottom of the equation, representing total variance, is the square root of the standard deviation of group 1 divided by n, and the standard deviation of group 2 divided by n of that group. So that's what we're actually doing. Total variance on the bottom, difference between the two groups on the top. Now, before we move forward any further, it's probably a good idea to talk about where these numbers are coming from. So the t-test is using descriptive statistics, mean and standard deviation. And we use mean and standard deviation when the data is continuous and normally distributed. That's why one of our assumptions of the between subjects t-test is that our outcome is normally distributed. So in the case of mean, we're simply summing all the scores of our dependent variable divided by the total number of participants, and we're doing this for each group. We're also going to do something similar looking at standard deviation, assuming that the slides will move forward to standard deviation, which it doesn't seem like they are doing. That is very annoying. If I hit the button again, let's see if we move forward. There it is. Okay. So again, measuring variability, standard deviation. I'm not sure why that took so long to transfer forward, but I'm just going to move forward with this discussion. So standard deviation is often referred to as either SD, and sometimes you'll just see it as capital S. And it's the amount of variance in a set of scores. So S or SD, the larger the S or the SD, the greater the variability. And mathematically, it is the sum of every individual score minus the mean squared divided by n minus 1, and then we take the total of that and we take the square root. That gives us standard deviation. Again, it's most frequently used with normally distributed continuous data. So that's where we're getting our standard deviation. Again, for the standard deviation, we have to first know the mean of each group. We then sum the sum total of everyone's individual score minus that mean squared, divided by the total number of people in that sample. Notice small n, so this is a sample. If I've got 20 total people, but only 10 people in group 1, I divide by n, which would be 10 minus 1, I divide by 9. And once I have that value, I'm going to take the square root, and that becomes my S or SD, my standard deviation. So let's walk through a quick example here. We have a raw score from two groups. We have an IV with two levels, and we have the N number of each group, mean and standard deviation. So group 1 has no caffeine, group 2 has access to caffeine, and we're looking at anxiety scores. So the anxiety scores of group 1 with no caffeine are listed here, 12, 14, 10, 8, 16, 5, 3, 9, and 11. So if we take a look at that, that means there's 9 total people. The mean is 9.78, and the standard deviation is 4.12. Our second group's anxiety scores, those that were taking caffeine, 21, 18, 14, 20, 11, 19, 8, 12, 13, 15. Our N here is 10. Our mean is 15.10, and our standard deviation is 4.28. So just taking a look at this, we can look at the mean of the first group, no caffeine. Their anxiety was 9.78 on average. And the group 2, their mean was 15.10. So we can see there is a larger difference. We're seeing more anxiety from group 2. The question is it statistically significant difference? And that's where the t-test comes in. Did we find a difference that just was due to random chance, or did we find a meaningful difference that we can be fairly confident in? So we're going to hand calculate the t-test, knowing that groups 1, N was 9, their mean was 9.78, and their standard deviation was 4.12, and group 2, the N was 10, the mean was 15.1, and the standard deviation was 4.28. And we're just going to plug those numbers into our equation. So our mean at the top is 9.78 minus 15.10. And on the bottom, we have the standard deviation of the first group, 4.12 squared, divided by 9, and then we have adding that to the standard deviation of our second group, which in this case is 4.28 squared divided by 10. So if we go ahead and just start running those numbers, we're going to start seeing that we take the top and it becomes a negative 5.32. The 4.12 times 4.12 is 16.97. 4.28 times 4.28, that's what squared means, is we're simply multiplying the number by itself, is 18.32. Taking those numbers one step further, we're going to do that division. 16.97 divided by 9 is 1.89. 18.32 divided by 10 is 1.83. We're going to add those together, 3.72, and we're going to take the square root, which is 1.93. So our t is now negative 5.32 on the top, the difference between the two groups, divided by the total variance, which is represented by 1.93. So if we take that, we find that our t is actually negative 2.76. Remember, the positive or negative sign of t simply reflects how we coded the groups. If we wanted to make sure that this was a positive number, we just flip group 1 and group 2. Our degrees of freedom is n minus 2, the equivalent of the first group minus 1 plus the second group of minus 1. So again, we have 19 total people, 9 in the first group, 10 in the second group. So 19 minus 2 means a degrees of freedom of 17. And again, if we're not allowing SPSS to calculate this for us, we now need to actually look at charts of probability to see, is the t of 2.76, positive or negative, at a degrees of freedom 17 significant? So we're going to find on our degrees of freedom chart that 17, we're going to find our significance of 0.50, 0.05, and we're going to find that the actual number that we need to see exceeding the critical value is 2.110. So the degrees of freedom 17 tells us our critical value. What we need to see a t above is 2.10. And in this case, negative 2.76 is greater than 2.11. It's significant. And again, sign is just a reflection of which group is labeled as group 1. We can ignore the sign in regardless to strength. So when we're looking at this, it's not actually a negative 2.76. We're just taking 2.76. 2.76 is larger than 2.10. We can say this is significant at a p-value of 0.05. Now, if we look at that chart and ask, well, what about less than 0.05 or 0.01 or 0.001? We can follow that over and see that for us to have a p-value of less than 0.01, we would actually need a critical value of 2.898. So it would not be significant at that point. And if we wanted to find a p-value of 0.001 or less, we'd need to see a 3.965. So this also tells us how significant it is. Now, again, when we're talking about how significant, that has nothing to do with the effect size or how strong it is. It's just how confident we are in that score. In this case, we're confident. We hit the bar of 0.05, but that's about it. We did not hit a bar higher than that. We did not hit 0.01 or 0.001. So the main points, the independent groups or between subjects t-test is appropriate when comparing two groups who consist of different unmatched participants, hopefully randomly assigned, but not always. When interpreting the results of an independent t-test, we need to consider, is it statistically significant, how the group differs, so how they were coded and what the means are, and the effect size, the absolute difference between mean and the Cohen's d. So hopefully this gives you an overview of what we're doing with the between subjects t-test, otherwise known as the independent groups t-test. We'll also talk about the other types of t-tests in other lectures.